Okay, we are ready to complete a hypothesis test, and we're going to start with what's called the traditional method of hypothesis testing. And we will be beginning with testing claims about population means, where the population standard deviation sigma is known, and this will allow us to use a z-test, and we'll get to all that as we jump into the example. So Chester advertises that his churros have a mean of 300 calories with a standard deviation of 30 calories. A consumer advocacy group claims that the mean is greater than 300 calories, and so they are going to head out to investigate. So let me go ahead and start with writing our hypotheses. So in this case, H naught, our null hypothesis, and H1, our alternative hypothesis, and we do colons after those. We start with writing our claim, which is our alternative, or it's also called our research hypothesis. And the advocacy group claims that the population mean is greater than the 300 calories that Chester advertises. The null hypothesis will be that same parameter, but always equal here, and the same value that appeared in our alternative hypothesis. Okay, so in hypothesis testing, we always start with assuming that the null is true. So when we start our test, we assume this is true at the start. And then the advocacy group is going to go out and get some data to determine if there's strong evidence against this hypothesis, which would mean they'd be supporting the claim that they're making. So we're looking for evidence against the null. So this is why when we start with our graphs, the mu value in the null hypothesis is in the center. So we're assuming that is true. So I'm going to write down here in the given, that's the mu value that appears in the null hypothesis. Okay. So coming up to my pictures here, the null hypothesis. And then they go out and get data, and they're going to look at, I'm going to label this axis over here, they're going to look at sample data, and they're going to figure out where their sample mean falls relative to 300. So if they think that the mean is higher than 300 for the whole population, then when they take a sample, if the mean is higher, they should expect a sample mean significantly higher. So we're not just looking for a little bit of evidence. So values close to 300 are going to be pretty likely. So that's the idea of a bell curve. But at some point, if we get a value very extreme, in this case, very far to the right, so values out here, far to the right, are called significant. So a significant statistic would be 1 X bar in our case, that is very far to the right. So what does very far to the right mean? Well, we have to determine that ourselves, how far to the right makes a finding significant. And that's going to be determined for us. It's called the significance level of the test. So that's going to be provided as we continue to read the given information. So a significant X bar, and we'll figure out this cutoff for what makes a finding significant in a moment. All right, so the group went out and took a sample of 10 churros. I'm going to keep writing some given information. They took a sample of 10 churros, and for the sample mean, they got 320. The population standard deviation, sigma, is 30. So sigma is known. And then based on this sample, do they have enough evidence to support a claim that the population mean for all of his churros is greater than 300? So theoretically, they think that the mean may be a higher value, not 300, but something higher. So this is our alternative hypothesis, they're not stating exactly what they think the mean is, just in theory that it is a higher number. Okay, so then it says, in other words, so it's a sample of 320, statistically significant, and they're going to use a 10% significance level. So alpha is going to represent the significance level of the hypothesis test, and it's our threshold for an outcome that is statistically significant. So I'm just recording my alpha there, and I'll go ahead and write it in decimal as well. Okay, so they think that the population mean is higher than 300. So this is what makes this a right tail test, because values that would convince them would be X bar values to the right. So that's called a right tail test. And then let's talk about the significance level. So in a right tail test, the area to the right of what we call a critical value, I'm just going to abbreviate it here for a moment. We're going to have a critical region and a critical value. The area to the right of this critical value, which will be a z-score, a critical value, the area to the right of that is going to be our value for alpha. So in this case, 10%. So basically, the critical value for right tail test will be the z-score that separates the top 10% of the graph from the rest. So to find a z-score, we need to know the area left of it. So if we take 1 minus our alpha, 1 minus 0.10, that will be 0.90. So now we can find that critical value, z, using inverse norm, because we inverse norm the area to the left. Okay, so we'll go ahead and inverse norm the 0.9, and I'll round to 2 places, 1.28. All right, so CV is an abbreviation here for critical value. All right, so when I draw that, I always like to switch color here so this stands out. So the critical value, that z-score 1.28, separates the top 10%. This is my alpha, 10% of z-scores from the rest. I'm just going to add a little up here. So this area to the right of the critical value is alpha. And the z-scores that make up that region created by alpha is called the critical region. So critical region, I'm just abbreviating CR. So the critical region are the z-scores that make up that shaded area. And then we'll also have a non-critical region, the unshaded area. And I'll write the whole thing here. I'll say non-critical region. We usually just abbreviate it NCR. So we have a critical region shaded, a non-critical region unshaded. And just to add some more vocabulary, sometimes you'll hear critical region referred to as the rejection region. The reason for that will be clear here shortly. So rejection region, so this will be the non-rejection region. All right, so this is traditional method. We establish a critical region. In this case, it's in the far right of this graph. And then we look at our sample mean and we figure out if it's made it into this region, those findings X bar out in this shaded significance level alpha region are called significant findings. So we're going to take our X bar, and in order to figure out where our 320 is on that axis, we're going to switch it into its z-score, and that will allow us to graph its location. So a test value is the z-score corresponding to our sample mean. So test value, I just do TB here, test value, it's also called your test statistic, in this case, our z-score, that corresponds to our sample mean of 320. So I'm going to give you the formula to convert our x bar into z. So x bar minus mu over sigma over the square root of n. So you might remember our z-scores from earlier when we had x, not x bar. The formula was x minus mu over sigma. But now we're not looking at the distribution of x individual churros. We're looking at the distribution of sample means. And so that's why that's an x bar. And that's why our denominator is sigma over the square root of n. So that was the central limit theorem that described the standard deviation of the sampling distribution. All right, so there's a lot of vocabulary for you, but let's go ahead and substitute. So I'm just going to do this across the page in a way that I know all calculators will work. You can always substitute and enter on your calculator then in any way you please, but I'm going to enter it as my x bar minus my mu. I'll do that in parentheses. Divide by, I'll open parentheses and then do my denominator. So 30 over square root of 10. Okay, so I'm doing my numerator in parentheses and divide by, and then I'm doing my denominator in parentheses. And I can get lazy here and not close my parentheses at the end. So the calculator lets me get away with that. I'm going to round that to 2 places. So that's 2.11. Okay, so that's telling me that the location of x bar 320 corresponds to a z-score of 2.11. So we're going to go ahead and graph the z-score, and then I'll graph that x bar with it. So 2.11 doesn't need to be exact here, 2.11. The reason for plotting that z-score is that tells me where my x bar of 320 would be. And so now I can see that 320 calories is part of this shaded critical region whose size was the significance level alpha of the test. So we say that that's a significant finding because it's part of this area that's made up of the significance level of the test. So in other words, 320 is significant. It's very far to the right on the graph based on our stated significance level, meaning that I'm now convinced, because it's so far to the right, that the null hypothesis is not the case, that really the whole graph should be shifted higher to a higher mean. So in the traditional method of hypothesis testing, we say to ourselves, where does our test value lie, or where does it fall? Is it out here in the significance level region called the critical region, or is it here in the unshaded non-critical region? All right, so in our case, our test value falls in the shaded there in the critical region, also called the rejection region, because when we get something this far to the right in a right tail test, we say we've got really good evidence to reject that the mean is 300. So rejecting our null hypothesis. So rejection region, because if our test value is in that region, we reject the null. Okay, so I'm going to try to squeeze in a little bit more here at the top. So I'm just going to point here. So if I reject H naught, so if I reject this one, it's essentially then saying that this evidence is supporting the claim that was made. So when we reject one, we support the other. And we always reference the null, we reject the null, and then our conclusion will address our claim. So that's our last little bit here. So based on this sample of 10 churros, so again, we're just using a sample to draw a conclusion about a whole population. So this is not a perfect procedure since we didn't collect data from all the churros, but at least based on these, there is enough evidence to support the claim. So we're looking for this idea of, are we going to support our claim or not? In this case, we rejected the null, so there is enough evidence to support the claim that the true mean calories in all of his churros is greater than 300. All right, so mistakes can be made, and in particular, I'm going to talk here about something called a type 1 error. So the advertised mean is 300. Our sample mean was 320. We've decided that that 320 is big enough to make me reject the null hypothesis. However, it is possible for the mean to be 300 and for us to get a batch of churros that average 320. So we're not saying that this could not happen. It could happen. It's just that it would be highly unusual if the mean were 300. So we would expect to get numbers around 300 for X bar if the mean is 300. We could get 320, but it's so unusual that I decide that at a 10% significance level to say, I think that that one is wrong. I don't think that that's the mean. I think I've got good evidence the mean is higher. All right, so the chances that we do an incorrect decision in this case are 10% because we're going to reject the null anytime we're in this region that's 10% of the graph. We're going to reject that number if our test value is there. But we could be wrong. It is possible to get 320 calories. So that's essentially the ending point here, is just knowing that when you take a sample, it's not a perfect picture of an entire population. It was just 10 churros. And so there is always a chance of making a mistake. All right, and that is what we call the traditional method of hypothesis testing. So what we're going to do next is approach this problem using another method, but the idea will be the same. We'll just be making the decision a little differently, and we'll take a look at that method.